Okay, Dad, we were discussing
Yeah,
GE.
during the war, I worked at MIT, and when the war ended, I had a job offer from Arthur D. Little. My friend Howard McMahon had been working there for uh, several years during the war, and he invited me to join him, and I was uh, attracted by this. And about that time, another good friend of mine, Walter Stockmeyer, uh, was invited to, he had been, I think, at MIT, and I got an offer to join the faculty at Columbia. He also had an offer from GE. He chose to go to Columbia, and he told uh, the people at GE, I guess Guy Suits, that he decided to go to Columbia, but he suggested that they have a look at me. And so I got an invitation to come over to the research lab and was interviewed and shown around. I had been to the lab several times before because I worked with Langmuir and Schaefer during the war. I was given an offer by GE and decided to go there, and I'd been told that in their lab that you had considerable freedom. You could pretty much work on what you wanted to, and that sounded very good to me, and I decided that I would take advantage of it. And I came to GE. Your mother at that time was in Elizabethtown with baby Peter, and I,
So this was late 1945, maybe.
yeah, something like that, I guess,
Okay.
yeah. And when I got to GE, I was put in Abe Marshall's group in chemistry, and was uh, assigned a lab with Murray Sprung and Wolf. His first name I've forgotten, Wolf. And I started, when I got there, working on a problem that interested me, which was supercooling. I'd worked during the war on supercooled clouds and had done some work on that at MIT. Had a technique for measuring nucleation, and I thought I'd continue the work I did at MIT on nucleation of emulsions of water drops in oil. I found out that Vince was very busy working on the freezing of water, nucleation of water, so I decided to work on the nucleation of tin.
And this is Ben Schaefer, who was already there, right?
Yeah, Vince had been there for many years, working with Langmuir,
Okay.
and that's how I happened to go to GE.
Okay. So you wanted.
Later on, I went back and forth to Langmuir and Schaefer's, and when Vince discovered dry ice seating in his cold box, well, after that, why, they said, why don't you come over and work with us? We got lots of problems on this. And I said, fine, I'll do it. And so I moved out of the chemistry lab where I'd been, and moved in with Langmuir, Schaefer, and Dr. Katie Blodgett.
And what year do you figure this came about?
This came around, I guess, about 46 or 7, something like that.
Okay, so after you've been doing other stuff for a year and a half or so.
Yeah, I'd been working on tin. As a matter of fact, I had, I guess, published a paper on nucleation of tin.
Okay. Then how was it working when you started to work with Vince and?
Oh, it was fine. I had a lot of fun there.
Okay.
And I had an enormous advantage because Vince had devised the cold box method for his experiments, which was a giant step forward in technology, and I had the opportunity to use his cold box. And I worked trying to get data on how many ice crystals you got from dry ice. And it occurred to me that maybe if we could get something similar to, that had a similar crystal structure to ice, maybe that would be a nucleus for ice formation.
Right.
And using his cold box, I found that silver iodide would work.
Right. Well, you tried other substances first, right?
Oh, Vince tried all kinds of other stuff first, and so did I.
Right.
And
now, how did you excuse me? How did you happen upon silver iodide as the?
well, I did my bachelor's thesis at MIT in the physics department with Professor Bert Warren, and I learned something about X-ray crystallography, and with him we worked out the crystal structure of solid bromine at low temperatures.
Right.
And so it occurred to me that if we could get some substance that was very similar to ice in its crystal structure, maybe that would work. And I looked up the crystal structure of ice, the arrangement of the atoms and the spacing, and I found silver iodide was very close.
Okay.
When I first tried it, didn't work because the silver iodide was very dirty. It had a lot of other junk with it.
You had a contaminated batch of.
Contaminated batch, and I think a few weeks later I found out that silver iodide did work.
Okay.
And I was not looking for something to seed clouds with at all, by any means. I was just wondering if you got something similar, would it work?
Right.
And I found out it would.
Right.
And it came really as a very big surprise to find that even though the silver iodide particles were submicroscopic, as small as maybe 100 angstroms, they would still serve as nuclei. And it meant that even though silver iodide was pretty expensive, such small crystals would work that you could get something like, oh, maybe I guess 10 to the 16th crystals per gram, so that even though it was expensive, you could still use it.
Right. You didn't need a whole lot of it, you're saying?
That's what I say, yeah.
Yeah.
A little went a long way.
Right. And when you finally had a pretty pure batch of silver iodide, wasn't it, when you first did it, wasn't the result pretty dramatic when you?
Well, actually, I happened to have some iodine vapor in the cold box, and I found I could get enormous numbers of nuclei by making a spark between a couple of dimes. That would make a silver, very small silver particles, and they combined with the iodine and made silver iodide.
Oh, okay.
And then when I found that work, I said, gee, this must be silver iodide that's working. And then I got some clean silver iodide and found that worked fine.
Okay, so the thing with the dimes happened after you used the contaminated batch.
That's right, yeah.
Okay.
I had kind of given up on
So you really were right on track.
this idea, yeah.
Yeah.
And I was wondering, would metallic particles work? And I made metallic particles, small particles, by making a spark between various metals.
Okay.
And I found when I did it with silver, I got a whole lot.
Yeah.
And I found out it wasn't a silver, it was silver iodide.
What was the iodide just left over from other experiments?
I'd found lead iodide worked, and Vince and I had done some experimenting with lead iodide and iodine. We found iodine would sort of work sometimes it wouldn't.
Okay.
Apparently sometimes there were silver particles or silver containing particles in the air so that the iodine worked. But when I worked with silver and iodine, wow, you got a beautiful batch of crystals.
And then you showed your results to Vince Schaefer and...
Vince and Langmuir were gone. They were away somewhere at that time.
Oh, were they?
Yeah.
Okay, and what was their reaction to...
Well, they thought it was great.
Yeah. Yeah.
And after that, then the game was to, when we found out, gee, you could use this in the atmosphere, then I began working on methods for making silver iodide smokes. And I devised a lot of those and tested them and wrote papers on them.
Okay. Do you mean dispensers for the, you know, sort of, to make the smoke and...
Well, what I did was one way was to impregnate charcoal with silver iodide and then burn the charcoal and that would vaporize the silver iodide.
Oh yeah, how did that work?
Worked fine. And another way I had was to cover twine with a paste of silver iodide and glue and feed that into a very hot flame. And that vaporized the silver iodide. And then when the silver iodide vapor left the flame and mixed with the cool atmosphere, the silver iodide condensed to form enormous numbers of submicroscopic particles that would serve as nuclei.
Oh. Okay, good.
That clear?
Yeah, yeah. And then you started working on the... Didn't you do some work on the smoke machines itself and later on? And
Yeah, well, that's what I was saying. I had a scheme for atomizing
yeah.
an acetone solution of silver iodide into a hot flame, and the so-called spray nozzle generator, which are still the ones that are most widely used in cloud seeding operations. I also made pyrotechnics, fireworks, with silver iodide in it that would vaporize the silver iodide and make a silver iodide smoke.
Oh, so you actually made fireworks with the...
Yeah.
Oh.
And those are still used.
So sort of a rain-making fireworks then,
Yeah,
huh?
that's right, yeah.
Oh, that's pretty interesting.
There are companies that manufacture those now.
Oh, really?
Yeah.
And how is that? You set off many of these, or just a few of them, or how does that work?
Well, I was just trying to test them, on a small scale.
Yeah. Now, in these in these ways to get the silver iodide smoke into the atmosphere. Did you patent any of these?
I can't remember whether I got patents on these or not. GE.
Yeah, GE's funny. When you patent something, it goes through the company for.
Well, there's nothing funny about it, but it's no more than fair. If I mean, they hire you,
Yeah,
you come up
yeah.
with stuff.
You're working for them, so if
Yeah,
they get.
you're working for them, and so you agree, and it sure makes sense to. Sure, you can have it, but when it began to turn out that this stuff worked, and it was possible that people, if it snowed, people might say, if you've done something, well, boy, it's all your fault. You caused the flood or the accident.
So they're liable then.
So that the lawyers got scared to death.
Yeah.
And there were some, GE did take some patents out on silver iodide and dry ice, but I think they never collected a penny of royalty from anybody.
What was their, attitude towards this whole thing that was going on that was so dramatic?
Well, they had mixed feelings. It was good, exciting publicity
Right.
for what their research could do.
Yeah.
And it brought them a lot of favorable publicity. But the downside was this business that maybe this could cause trouble.
Right.
And maybe it could take them to the cleaners because they had deep pockets and would be a very attractive target for a lawsuit. And even if they could successfully defend themselves, why they could incur enormous legal bills.
Right. Right. So there was still a lot of unknown variables involved.
Yeah.
Okay.
All this thing is well described in a thing that we published a while back after I came here. We published a report that was generated by GE on the history of cloud seeding. It was written by Barry Havens. And Barry Havens and Jim Justo, professor at Albany in atmospheric science, the three of us published this thing under the title Early History of Cloud Seeding, which is a good account of this. Barry Havens went around and talked to Vince and Langmuir and everybody involved in it, and then started writing it, and then when he'd get something written, he'd bring it around and said, how's this? And we'd all look it over, and sometimes we said, no, it wasn't like this, but he worked on it until everybody said, yeah, this is the way it was.
Right.
And that's a good publication that describes everything.
Okay, and the title of that is again, Dad?
The title, originally, this came out as a report. It was called The History of Project Cirrus.
That's how I know it, yeah.
And then we changed it to Early History of Cloud Seeding.
Okay. Now, how did the name Project Cirrus? Just because?
I forget who thought that up. I think Navy Commander Dan Rex, who worked on this project. GE got funded by the Defense Department.
Okay.
The Signal Corps, the Air Force, and the Navy got together and formed what became known as Project Cirrus, which was an exercise to test out these new technologies that had been developed.
Okay. Now, isn't it your feeling, Dad, that in the beginning that there was a lot of people are sort of hesitant about the use of cloud seeding and actually, a little scared of it. Isn't it your opinion that, it's been how many years since you first discovered silver iodide worked very well in cloud seeding, and isn't it your feeling that this could be used and should be, tested and experimented more with, and it could be
Well, it was Schaefer and Langmuir made a brilliant innovation. They showed you could, at a pretty modest expense, turn very large volumes of supercooled clouds into ice crystals. At that time, just about everybody in meteorology thought that the only way you could get rain in the atmosphere was first to get ice crystals, which would then melt
right.
and form rain. And they thought all rain came this way, and that was the only way you could get it. Well, when Schaefer found out that he could turn a cloud into ice crystals, well, then that looked like, well, there's the answer now. We can make rain anytime we want.
Right.
And of course, it turned out that things were not nearly that simple.
Right.
But a lot of rain is formed that doesn't involve ice crystals at all.
Okay.
And people immediately decided, let's put this powerful new stuff to use and try it out and see if we can't get more rain. And so what started out with some very nice experiments with very simple experiments, making holes in supercooled clouds. Following that, people said, forget this long hair stuff, let's make rain, because that's important.
Yeah, people wanted miracles right away,
And a whole lot of people started work to develop rainmaking. And a lot of government funding was supplied. And I think, as I understand it, $100 or $200 million got invested in this rainmaking business. And it was just a pragmatic attempt to see if you could make rain. And ultimately it involved the work of statisticians trying to figure out, did we do anything or didn't we?
right.
It's impossible to predict with any accuracy how much rain's going to fall in the absence of cloud seeding. So you can't tell very well whether you did any good or not.
Right.
But the initial experiments, when they made these holes in clouds and examined them and figured out what was going on, those experiments have not been continued, and they should be, particularly now that we have satellites where we can see what happens.
Yeah, it'd be a lot easier to detect exactly what's going on.
That's right, yeah, and to get as simple a situation as possible, so you begin to have some understanding for one part of it. But this rainmaking involves a tremendous variety of situations.
But you feel that not nearly enough research has been carried on in this, right?
As a matter of fact, I'm thinking of writing a proposal to get this research going again.
Yeah, that's sort of been put on
using the satellite.
Yeah.
To analyze it.
Yeah.
To see how big a hole do we have to make to last 12 hours.
Right.
And how does that hole affect subsequent meteorology?
Right. Now, would Doppler radar, play a part in this?
Everything would help, yeah.
Yeah. But you're saying that the technology...
I would like to do the seeding on these situations when you have stratiform clouds going hundreds of miles in either direction. And then carve holes in it and see what happens to them and learn how that works.
That's something a satellite could pick up pretty easily.
Yeah. In the work to GE, why they would just watch it for an hour or so.
Right. And the satellites weren't involved. That was like from Mount Greylock and other areas.
Well, they would. The Greylock was just an isolated cloud seeding, but
Yeah.
there were these stratiform cloud seedings that were done.
Well, where were they done at?
Oh, they were done over the eastern U.S.
Oh, really?
and over the ocean.
But in recent times, nothing has been really done similar
Very
to.
little, but about all that's been done is to clear airports.
Yeah.
Super cool fog.
Yeah. But your friend, is it Tom Henderson, is doing some pretty good stuff out in.
Yeah, Tom is seeding. He's rainmaking, and he's learned how to do it quite well. And he tells me they've had some very impressive results the past few winters in seeding systems that come off the Pacific before they go over the coastal range, and he seems to be putting more water in their reservoirs.
Well, that's interesting. So there's still a lot to be done, you're saying?
Yeah, there sure is. Yeah, I feel that it's too bad that they got into the real complicated stuff without first and neglecting the beautiful, simple experiments that Langer and Schaefer pioneered.
Okay, Dad. Well, I think we'll end it right there and continue some other time.
Yeah.
Okay.
How long did you go?
We went for a good 20 minutes, I think.
Huh.
Okay, thanks, Dad.
Okay, thanks.
We're trying out a new camcorder that was just purchased.
Bill.
Yeah.
And
Don't do that.
I told Dunk about it, and he said, was he making a recording? I very much doubt it.
Yeah.
And I got thinking there's a lot of that I'd like to get on the record. And it occurred to me that maybe set up a camera. And I find this business of talking with somebody very simple. And if I sat down to review what my thoughts were on everything, I couldn't do it. But if there's somebody there keeping me going, why, it's an easy thing to do. And I asked Dunk if he'd be willing to do it, and we're going to get this thing set up. And so if I sit down with somebody at a certain place and turn on the camera, why, we can do an interview whenever we want. And Kurt has rigged this up in the living room. And I think sometime, now or tomorrow, we might try it out. I'll go sit in my position, and you, Fiona, or any of the kids can come in and ask me questions, and it'll be on record. And later on, it will be of interest to see what things were like, particularly what people were like back then. And so whenever you want to do this, I'll give it a try.
Go ahead.
Today is the
Wednesday the 26th.
today is Wednesday the 26th, 1997, and Duncan and I are going to talk about various things, including cloud seeding, and I will lead into things. And Dunk has just appeared, and this morning I've been occupied with various things, and I was going to make a decision about my wardrobe for this recording. And one of the problems is my hair, and so that
Hey, you're all set for summer.
I'm all set for summer. Yeah, I began looking pretty good by then. Well, I think that this is preferable. At least it can be duplicated. I won't have to adjust my hair each time we break off. Well, I realized my hair was getting pretty long in the latter part of December, and I realized that I should have a haircut before I went to San Francisco to give my talk. And
It's the AGU meetings.
yeah, at the AGU meeting, and I went into Dan's place and to get a haircut. I think he was there, and there was a woman there, and he said, she would cut my hair, and I sat there, and this woman cut my hair, and
That's Maria, the young girl.
I had had a couple of several haircuts from Maria, and was well satisfied with her work, and I wasn't sure whether this was Maria or not, but she gave me a haircut, and when it was done, well, I looked at it in the mirror, it looked fine. I got home, and then a while later I realized that there was part of my hair that she had not cut, that there were some pretty long strands, and I found that properly combed, why, it looked great. But it was a damn nuisance. usually with my haircuts, it makes a big change because I let it grow pretty long, and when it gets cut short, why I don't have to do much with it, and it doesn't get so messed up when I put on a hat and take it off. And well, a week or so ago, I realized that I ought to get another haircut because there was this real long strand, and then the rest of it was quite long. And I mentioned this to my son Alex, and as we were coming back from radiation therapy, Alex said, "Oh, let's over here. Let's go into the university and get a haircut." And I explained to him that you need an appointment to get a haircut, and he said, "Well, we'll give it a try." And we went in and went down to the place. For a moment I didn't recognize it. Everything had been moved around and so on, and there was this woman there, and she said, "Dan isn't here now. He'll be back in a while. If you'll wait a few minutes till I get through with this guy, why, I'll give you a haircut." And I said, "Fine."
This is Maria.
Let me tell
Okay,
the story.
okay.
Okay, well, I sat down and began talking about what kind of a haircut it was, and I told her of my experience there a while back when this woman had given me a haircut and left this long lock of hair, and that I'd found it annoying. And it developed that there was no other woman working there, and this was Maria.
Well.
I was bitching about this other haircut.
So your face.
Which it turned out that she had given me. Well, I find it difficult to recall the details of our conversation, but I tried to smooth it over as best I could. And she was really forgiving, and then I remembered her name and everything. And
You gave her a bigger tip than usual.
yeah, you bet, we did. And I gave her the specifications for the haircut. I told her, well, you understand now, I just sort of want it off generally, and well, the way I'd like to have it, I want the kind of haircut in which the difference between having it combed and not having it combed is minimal. And I find that I think she did an excellent job in meeting those specifications, but I am worried that maybe she got even with me too. So that's the story on my haircut. And the reason that this thing is set up, we have this recording, is that I guess a week or so ago, I think it was on a Friday, we can figure out the time if necessary. I guess first time I got back to the university, I found this message on my phone. It was Peter Hobbs, who's a cloud physicist at the University of Washington in Seattle. And Peter said that he would like to talk to me about some stuff pertaining to cloud seeding, the early time of cloud seeding. And so I took down his number and came home, and I thought it'd be very interesting to talk to him. And before calling, it occurred to me that it'd be worthwhile putting this on his nickel. And so I decided to give him a call, establish communication with him, and then to ask would it be convenient if he called me another 10 minutes. And well, first time I dialed, I got him, and he started talking.
So it was on your nickel after all?
Hmm? Yeah, it turned out that way. I got started talking, and forgot all about it was called back business, and by the time the phone conversation ended, I think I had a splendid bill. And in talking with him, I told him a lot of my thoughts on it, and I told you a bit about it, I think.
So he wanted to call you to ask about the cloud seeding, and
yeah, well, I told you about my conversation with him.
you did a bit, yes.
Yeah, and after this long conversation, well, I got thinking, gee, I should have mentioned this too, and I told you about it, and you said, did he make a recording of it? And I doubt very much that he did make a recording of it. And it occurred to me, well, why don't I make a recording of it? And I'm glad that you agreed to come over, and we can go over some of the business that I talked about with Peter, yeah. And I guess that he had talked to Sally too, and that it turned out, I guess, he was sort of, it sounded like, dimly aware of the publication, Early History of Cloud Seeding, and I think Sally sent him a copy, I believe. At any rate, when he
She sent him a copy in just the past month or so?
Yeah.
Okay. I'm surprised he was not aware of that.
Well, maybe he had it, I didn't.
Forgot it.
At any rate, Sally did send the thing to him, and he began, one of the things came up early was he was kind of curious that, about after the work at GE that was I much involved in cloud seeding, and I guess that he was asking about Vince too, and he was aware, I guess, that I hadn't done much work in cloud seeding afterwards, and he wanted to know how much Vince had done. I wasn't really sure how much he'd done. I got it's my recollection that he didn't make much of a distinction between the term cloud seeding and rainmaking. That I believe he got the impression he used them almost interchangeably. And I think that early in the discussion I tried to explain to him, and I loaded to him on this business about does cloud seeding work or doesn't it? And this question is frequently asked, and pointed out there's a very definite answer to that cloud seeding works all the time under certain clearly specified conditions. You can turn a lot of cloud into ice crystals at low expense. And the thing went on, and he, someplace along the line, that he wondered why cloud seeding was a failure, or why rainmaking was a failure. And was that the reason I got out of it, I suppose. And I asked him, what do you mean it was a failure? And I guess there was some big book put out, I believe in the 70s, by Bureau of Reclamation or something, I guess Peter thought that the way things had gone, that it turned out that cloud seeding hadn't lived up to its promise at all.
I'm not familiar with this book.
I'm not at all either. I'll have to look. And well, all this stuff is kind of jumbled. I don't remember the sequence, but I was pointing out to him that I think that cloud seeding operations are being carried out, I think, in 60 or 70 countries now, and that it's a pretty good-sized, stable business in the U.S.
Did you point out to Peter maybe he should contact Henderson?
No, I didn't. I certainly should have. This is one of the things that I should have done that I didn't do. And then I guess he was asking the question, why has cloud seeding been a failure? What is the reason for that? And well, I guess then when we got into the business, how do we know it's failed? And I got into the business that I think that my own view is that cloud seeding has fallen far short of some of the original expectations, because even though I think it runs to about $100 or $200 million has been spent on cloud seeding research.
We're talking now about the United States.
I'm talking about the United States, yeah, really.
There's a lot more. A lot more has been spent in other countries.
Okay, I was thinking only of the U.S. And I explained to him, well, he asked me, what do you think the reason is that it's failed? Well, I objected to that sort of question. Just I don't think it's failed, and I hope I got that through to him. And I explained to him that I thought that all this money had been wasted on trying to answer an idiot question, something of that sort. And he was puzzled what this idiot question was, and I said, this idiot question was, does cloud seeding make more rain or doesn't it? And I found out that this was quite puzzling to him.
Because he is equating cloud seeding with rainmaking.
Well, no, but whatever it means. I mean, the question is, does cloud seeding make more rain or doesn't? And I said that, well, if you ask that question, it can give you a yes or no answer. It works. It does make more rain under certain circumstances. Well, but then they say, well, it doesn't make enough. Or when you want, in other words, you get into the economic side of it. And so that you're not asking a scientific question, you're asking a perfectly valid economic question. But I explained to him that at the beginning of following Vince Schaefer's discovery that you could make an awful lot of ice crystals with a very small amount of dry ice. Schaefer and Langmuir understandably became very excited, and Langmuir began giving it a lot of thought. And Vince transformed the little cloud over Mount Greylock into ice crystals, and then Schaefer and Langmuir began thinking up something to do. Well, Langmuir, in his history, I think, has mostly been involved in wondering about something, a lot of it in the lab, and trying to get the simplest possible situation that he could, so to minimize the number of variables that he was dealing with. And using going along these lines, he was able to conduct experiments and come up with wonderful generalizations on the behavior of things that have proved very durable and worthwhile. And with the cloud seeding, they came up with, I'm sure, with the idea of getting something simple. And the very simple thing in meteorology is, which is pretty complex, is stratiform clouds that stick around for long periods of time. And these situations occur pretty often in the Northeast. And when they got the Project Cirrus in the airplanes, Langmuir calculated from the number of ice crystals that had been measured in the coal box. We had some idea how many ice crystals you could get from a ground of dry ice. And on the basis of these estimates, he figured, well, maybe if an airplane flew along and dropped so many grams of dry ice per mile, that that would be enough to have an effect. And designed, say, well, let's fly a certain pattern, and they conceived a very simple experiment and carried it out. And it did pretty much what he expected. It made this line that grew and spread, and they had all these pictures of it, and then Langmuir sat down and analyzed the pictures in great detail and determined the rate of growth, and then he would make guesses and calculations on what should be the rate of diffusion, and then look at the amount that the heat release that caused the little additional convection, and he looked at it every which way.
Now, I don't think this has been published officially, but his occasional report number 10 of Project Cirrus spells this out beautifully. About a flight they made over Cape Cod Bay, and he did in great detail just what you described.
Yeah.
I was looking at it a couple of weeks ago, and it's a pity this was never officially published, but it should be.
I am not sure how much of this is in print, but for sure, he sure understood what was going on, and I remember the learning these little things from him, that the amount of precip you get should vary as the square of the cloud thickness, and also that he was pointing out that the heat that is given off when you see clouds is given off by not only by the transformation of the supercooled drops, the water that is in the supercooled drops. When that turns into ice crystals, why that gives off a significant amount of heat, which can cause convection. And then he also pointed out that there's not only that heat, but the heat that you get from precipitating a lot of the water vapor in between the drops. And in some cases, that's all there is. I don't think that people were recognizing this for several years after Project Cirrus. But
Vonnegut mentions this too in his occasional report number 10.
well, I'm sure. I
He
mean,
talks about drying the cloud out completely. Of course, if you use up all that water vapor in between the
yeah,
crystals.
yeah. Well, he understood an awful lot of this before the experiments were done. A lot of this he didn't learn from the experiments, but he had anticipated it. And the stratiform seeding was beautiful science. It was wonderfully planned and analyzed, and Langer and Schaefer began talking about experimental meteorology, and it was experimental meteorology in the best sense of the word. It wasn't doing this and that and see what happens, but it was getting as simple a situation as possible and planning as best you could in advance to ask questions and do it. And they opened new doors, and this hasn't been taken advantage of at all. That what happened was that about this time, everybody realized that the cloud seeding was of enormous importance because there were droughts and one thing or another that mostly people needed more rain, and at this time almost everybody believed that the only way you ever get precipitation was by first forming ice crystals and then having it melt and getting rain. And with Schaefer's discovery, why it became obvious that, gee, now that we could make ice crystals whenever we want, why it should be possible to make rain. And the machinery was set in motion to take advantage of this wonderful new discovery. And people decided to make more rain in a certain region, so they would get an airplane and drop dry ice into it, or maybe make silver iodide smoke and see how much more rain they got. And when when these experiments were conducted, why things were a little confusing because they didn't have a very good idea how much rain would have fallen if they hadn't done the experiment. And so they finally decided that they would have to do it statistically.
Or use a control experiment.
Or use a control, yes. And to determine how effective it has been on the basis of these experiments. And these experiments involved seeding supercooled clouds. And although there was every reason to believe that the clouds were not all the same, even though they were supercooled, the behavior of the cloud, if no seeding had been done, would have depended very much on the population of condensation, nuclei and so on. It would also have depended on the concentration of natural ice-forming nuclei which were present. And there cannot be the slightest doubt that many seeding operations are carried out where the seeding operation is a drop in the bucket. One couldn't possibly expect to see it above the noise because there are such wide variations. And if they did realize that, decided that they were practical people, and that the thing was, they wanted to find out whether it worked or not. And they carried out these operations without knowing, without having the capability of knowing anything really about what was going on. These enormously variable things. And as the result of the expenditure of $100 or more million, what we've bought is a bunch of correlation coefficients, giving the probability that the seeding did something. And I think it was an idiot waste of money. But at that time and today, we haven't the remotest idea how precipitation is formed. I mean, we know a little bit here and there, but there are all kinds of important things going on that we know nothing about. But the feeling has been, well, you really don't have to know if you get a big enough sample. Mm-hmm. And well, I guess now is a place to break off.
Yeah,
so I'm glad to have this opportunity for...
This is all the more reason, I think, that some of Langer's ideas, that occasional report number 10, be somehow gotten into the literature. Because what you're describing here, he's talking about in that report. I had not looked at it for years and years, because it was missing in my collection. But Sally got it for me about a week or two ago. And I went through that, and wow, all this talking about, of course, the heat being released, and he's talking about the spreading of the seeded line, so many meters per hour or whatever.
Well, let me continue just a minute and lead into the next installment.
Okay.
Things have changed a lot since those seedings, since Langmuir's work. One of the biggest is that we're no longer limited to watching these seeding things for an hour or so, but we have satellites and can follow them for long periods of time and cover large areas. And you could conduct much larger seeding operation, find out how big a one you have to do before you have affected the weather tomorrow or someplace else. That seeding is no butterfly wing. And I think that another thing is that there is a wonderful opportunity for the use of computers to do this, and already in the initial work that Langmuir and Schaefer did on their stratiform seeding, there's enough basic information so that somebody with a modern day computing facility should be able to do what Langmuir did in detail, and to see how well can they predict what would have happened, how close can they come to predicting what has actually been observed. And with this groundwork, it looks as though they began to get a feel for it, and then they could predict, well, suppose we make the seeded area 10 times as big, or if we use clouds at a different temperature, and so on, then you could begin to make computer extrapolations. And this stratiform stuff, seeding, should be continued, all aspects of it.
Amen.
Okay, maybe that's all I had to say about
Right now.
about seeding right now, but thanks. I hope it's worked out.
Yeah,
And we have a record of
Sure,
it.
sure, we can continue this
Yeah, I'd like to if you would.
tomorrow or whatever.
Okay.
Okay, till next time, fellas.
Yeah.
Until next time.
Okay.
Yep, you're
All
going.
right. It's now the 27th of February, about 20 minutes to 11. And I've been thinking that this business I'm doing here is somewhat related to a phenomenon maybe you're aware of it, that I understand that when people dealing with trees want to get seed, they get an old tree and put an iron band around it real tight, and in a little while, as the tree grows, why it's constricted by this tight iron band. And I understand that with this treatment, why they makes the tree really put out seeds.
I've never heard of that. New to me.
Well, maybe this is a little bit like that. And last time I spoke about the opportunities we now have for meteorological experimentation with simple big systems, and what with satellites, computers, and so on, could do an awful lot. And a while back, I don't know, 10 years ago or so, I was thinking about this and decided to try to do something. And from time to time, I talk with Tom Henderson about this, and he thinks that it's a fine idea. And a while back, I noticed on the satellite pictures that in the beginning of winter or through the winter, you get polar outbreaks, very cold air, and it comes over the U.S., and then along the eastern seaboard, you can see that there is a clear region offshore, I don't know, 50, 80 miles, I guess. And then there is a uniform cloud that by the time the cold air gets out so far, why, enough mixing has occurred, and there is a cloud has formed that I think extends for large distances. And that presumably is a supercooled cloud, and it is very uniform. And I decided to carry out an experiment in which I would, when one of these occasions occurred, I would go to the seashore and down near it and turn on a silver iodide burner and see whether downwind we could see something. And I talked this over with Lady Johnson, and he agreed it'd be fun to do. Tom Henderson sent me one of his silver iodide smoke generators, and we waited for a suitable outburst of cold air, and made arrangements, I think, to preserve, obtain satellite images so we could see if we did anything. And I guess in the middle of the night, Lydia and I set off in my station wagon with the silver iodide burner and propane tanks and stuff, and we finally, first, I guess we stayed overnight in a motel, and then I guess around Gloucester, and then I think let some silver iodide smoke off Gloucester. Miserable weather, cold, very windy, and but we got the burner going. I was not too pleased with the way it operated, but it was burning. And
right along the shore?
Yeah, right along the shore, yeah. And then for some reason we decided to go up north, and I think we got into Maine. And
how long did you burn it down there? before you decided to go north?
Don't know. And then we went north and did it again. We went east and did it again. And we operated for a few hours, and I guess we noticed that Cirrus was moving in, and I guess we decided to quit, and I decided to come home. And meantime, this acetone silver iodide solution had leaked somehow, and the interior of the car was stinking with this stuff, and well, it's it as a electrometer or whatever it is that makes tears come dry. I don't know what the chemistry is. It's not just acetone, but it was fierce. And we were driving along with open windows, and it was one of the worst expeditions I've ever been on. And when we got back and looked at the satellite picture, it developed that just when we might have expected to see anything, why it was all covered over by cirrus. Yeah. And I kept thinking about it, but never developed enough energy to do it again.
Well, clearly this is something that should be done again.
Oh, yeah.
I think it was something like this that was done in Project Cirrus. And Reimer wrote his report, the occasional report number 10. I think that was a similar situation, where there was cold polar air flowing out over
the ocean.
Bay.
Yeah, well, yeah, that's...
And there was straight cirrus, not cirrus, but
well, I
straight
think
flare.
In a situation like that, why, I talked this over with Tom Henderson, and I think that this is a situation you know pretty well is going to occur, and it is like a wonderful blackboard. And if he went up with his airplane with different burners on it and so on, and carve something here and something there, and watch it with a satellite, in a little while they could learn an awful lot about seeding.
If you were going to do it from an airplane, wouldn't it be better to use dry ice flying over the top?
Well, no, I mean, use everything. See how they all
okay, sure.
compare. And of course, use dry ice or anything. Well, dry ice is a good standard, of course. But there's too bad this stuff is not on the West Coast, and there wouldn't be much to this operation except moving the airplane to the East Coast and paying the living expenses of the pilot and so on. But I don't think I ever got to the point of completing a proposal. At the time, I would have been happy to go in with it, but it's certainly something that should be done, and I think that involving the computer people is very important to get them to see how well they can do, not in predicting what's going to happen to a cumulonimbus when you see it, but they're free to come up with anything they want. But we have enough information now, and the work that Langer and Schaefer did to see can they how good are they at predicting, and then if they got a little skill at that, why then they could extrapolate.
Yeah, as you point out, this is a relatively simple situation compared to cumulonimbus. Now it's like a blackboard again. You can write on it,
Yeah.
straightforward.
But I have a feeling that that if you do a meteorological experiment, that a meteorologist will say, well, this isn't like the real atmosphere. You didn't take into account wind shear and all kinds of things, and it seems to me that the more variables you have, why, the happier they are, the more realistic it is, and the more hopeless it is.
Agreed. Yeah, I've heard you talk about this a number of times in the past.
Yeah,
It's something that really should be done.
yeah. Could you get me that? I'm gonna see if things. Well, I have somewhat different thing to talk about, or we can talk some more about that, or whatever you think. You want to?
No, go ahead. I know you have different things you want
Yeah,
to
okay. Well,
bring
this
up.
is something I think about off and on. I as a graduate student, I had a course in the theory of solutions given by Professor George Scatcherd, who is an expert in this field. I did my thesis under him, and I had a very hard time understanding all this theory of solutions, and I think that a lot of my classmates did. And I remember a guy named Jack Kiger that said to Professor Scatcherd, he said, you know, I'm not stupid, I'm just slow. And I was thought that that maybe that applied to me. And over the years, I have can remember some situations in which, looking back, I was awfully slow. And one of them is in connection with cloud seeding and nucleation. As a result of working on nucleation of tin and supercooled water, I think there was a paper in which I recognize that if you cool a supercooled liquid down, why there isn't some temperature at which it freezes, but there's some temperature at which, if you lower the temperature, freezing becomes increasingly probable. And that, well, this, in other words, I had some understanding that nucleation was a stochastic phenomenon, and that if you have an unstable situation, if you wait around long enough, eventually, by chance, things will get into a situation where something dramatic gets initiated. It's like spontaneous combustion or whatnot, and I recognize that the freezing of supercooled water was like that, and I think that I was maybe calculating half-lives and stuff like that. And this work I did was before cloud seeding.
That's when you use tiny drops of supercooled tin or water?
Well, I started the emulsion, I started drop work and so on at MIT. At MIT I didn't recognize it. When I got to GE, I worked with, I'd have an array, a number of drops of water, and I'd watch, observe how they froze. And then also I used powdered tin and suspended in a varnish and follow its freezing with X-rays, or then I used powdered tin and followed it with a dilatometer. At any rate, I did analyze the behavior of sulfur iodide smokes at various temperatures, and you helped me.
I recall that.
In some of that work, and I realized that the sulfur iodide didn't work right away. It worked faster, colder it got. But sulfur iodide didn't cause the ice crystals to form. It just made the probability of formation higher. Well, in Project Cirrus, Vince discovered that sometimes there are very few ice-forming particles in the air. And sometimes it'd take air and make a supercooled cloud and have a hard time finding an ice crystal. Another time you find more. And then with the silver experiments with silver iodide, we found that we could get 10 to the nth ice crystals per gram. I mean, enormous numbers. And on the basis of those experiments, I concluded, and I think others did, that putting out the silver iodide would make an enormous difference. I mean, you could figure that just an infinitesimal amount of silver iodide would be enough to make nuclei to have an effect. And I think most of the thinking went on that way, that the signal to noise ratio of the seeding versus, I mean, the artificial nuclei we were putting in compared to a natural one was enormous. But nature really wasn't much good at all at making ice crystals. Now, when we tested the atmosphere to see how many ice nuclei are there now, we would put some air in the cold box, blow into it, and see how many ice crystals formed. And we would allow not much more than a minute, or less than a minute, for nature to do her work. And in some cases, if we saw such and such a concentration of ice crystals, we would be right. We would say, gee, there are only very few. But there would be other cases in which we might see the same number of ice crystals. But in those cases, there might be a lot of natural aerosol there. And at a given time, could produce ice crystals. And so we were giving testing silver iodide versus nature, and giving them both equal time. But in nature, they supercooled clouds persist for hours or days or weeks. And in the course of time, I mean, because there are a lot of natural aerosols there, why, it can just keep forming ice crystals. And so we vastly overrated the potential of cloud seeding, not recognizing that ice crystals form naturally at far greater, sometimes at far greater rates. Now, if there are no aerosol particles, yeah, and sometimes there aren't any, but other times you may be, the air may be have high concentrations of lousy nuclei that just keep making ice crystals and making ice crystals all the time. So this is a case where I feel that I was pretty slow in catching on, even though I was in possession of the information. I mean, I had found that it was a stochastic effect that had failed to understand the implications of that.
Well, if you were slow, Bernie, in catching on, hundreds of others were even slower.
Well,
So
are even slower. I don't think a lot of people understand that now.
That's yeah.
Yeah, no, I mean...
It's not accepted.
No, well, oh, that's right, yeah. But, well, there's one case, and there are other cases, and I'll discuss, but you want to say any more about the ice one, or should I go on to another one?
Well, you might mention that you have published a couple of papers on this particular problem you're talking about, the time delay and the production of ice particles. I know you've done some work.
Yes, well, I have for a long time been calling attention to the fact that much nucleation work does not consider one of the more important variables, which is time, which is of great importance. But in the beginning and until today, many people in textbooks pretend that every aerosol particle has its magic number, and you get to that and bingo, it makes an ice crystal. And above that, warmer than that, nothing ever happens, and below it, it's inevitable.
That's right, the time factor is not considered.
Not at all, no. And,
Well, they should take a look at a couple of these papers I know that you've done with some of the students.
well, I eventually recognized it, and I published on it, and I made every effort to get people to see my point of view. Just with modest success. Another situation in some ways is somewhat similar with that Charlie Moore and I got involved in doing experiments related to convective electrification, and an important part of the idea of convective electrification is that there are downdrafts in the upper part of thunderstorms that carry electric charge in the same way that the belt on a Van de Graaff machine does. Yeah, I never turned that on, I guess.
With that tape recorder?
Yeah.
No, we just have to
Just hope.
hope that the one with the video is working.
Yeah.
And Alex promised us,
I
and
hope
it would
the
be
thing
working.
is working. I don't know how you can tell sitting here.
I can't tell. Alex told me how to turn it off and on, that's all I know.
Well, I assume it's running.
I guess he's headed off someplace to pick up more tape.
He's gone down to buy more tape, and I think there is still some left. uh, uh, shall we stop now and then resume later
Until
sometime?
Alex, okay, until Alex comes back,
Or whenever.
or some other,
Yeah.
okay?
Maybe this is a good time to stop before I
Okay.
get involved in this other
Oh, let me find the button here.
Uh,
Here it is.
355. Last time we talked about cloud seeding, and to some extent began on convective electrification, and I don't think I did too much on that. And we can.
No, you didn't do very much. I think this is something that should be explored.
Yeah, well, should we do some more cloud seeding then?
If there are things that you'd like to explore.
Yes, there are
Go ahead.
things. Well, they are, I guess last time was confessions of being slow to recognize things, and in this one, going to be confessions of being wrong. There were times when I was wrong, and one of them has to do with the phenomenon that you can see in the cold box, that if you wait until a supercooled cloud, just until it is finally evaporated on its own, that a few little specks of dry ice will create enormous numbers of ice crystals from the clear supersaturated air. And I recognize that that took place, and did experiments showing that you could do this by get ice crystals by adiabatic expansion, and I guess many people suggested that that occurred. What was happening was happening in two steps. At first, the expansion made water drops, that they were the first phase to appear, and then that the water drops froze. And I think that there's something of a physical law that says when you have a phase change by it may go through a metastable state and then to the stable.
Okay.
And I was quite impatient with that, and figured, well, it didn't make any difference anyway. And I since recognize that this is very probably the way that it happens. And
we're going back to Project Cirrus days.
yeah,
You
back
say
to
you're very impatient with that idea. We're talking about the late 1940s.
or maybe into the 50s. And the question was, how does that happen? And for my purposes, it didn't make any difference. It just used to get enormous numbers, but I guess over the years, thinking about it, I come to recognize that this is unquestionably the way that it's occurring, and that when you put dry ice into a cloud, what you into a cloud of supercooled water drops. The first thing the dry ice does is to make a cloud of supercooled water drops, real small ones, which then turn to ice. And that if you have supercooled water, the density of water molecules is very high. But in the vapor phase, why, they are very rare. And in the vapor phase, that they should accidentally come together in the ice crystal form is remote. And so unquestionably it's happening. At first you get supercooled water, and then supercooled water can't be, you can't supercool water very far, and then it forms. And in Project Cirrus, I think that I got the impression that Langmuir and Schaefer felt that if you had a region had some air that was supersaturated with respect to ice, and you took that to -40, why all of a sudden you got all kinds of ice crystals. And well, I got thinking about that, and recognized that if you had air supersaturated with respect to ice at say -38, and cooled it to -40, you had ice crystals, why that didn't make any sense at all. It couldn't be that way, because you require considerable supersaturation. And then I suggested that Andy Detweiler do some experiments on that. And he found that this is true, that if you have supersaturated air, why, and we used cold BBs or something, he showed that, yeah, they had -40 wouldn't do the trick. It had to be way much colder. And then that would cause, you explain that first it had to have enough supersaturation to get the supercooled, to get the droplets to come out of the vapor phase, and they in turn would freeze. And
when Andy was doing this work, was this part of his master's thesis? No, it could be master's, I'm confused. He worked with me in the master's.
That's right. No,
this is part of his PhD.
He may have been a postdoc for all I know. But I suggested that he do the experiment, and it did clear it up for me, and I guess it would for others. And this got published someplace. In playing around with thinking about supercooled clouds, I got involved with Leedy Johnson, who found this very interesting. And he played an important part in my education by, I guess maybe he's the one that finally got through to me on the fact that the liquid drops formed sooner, and first, and then that they froze. But he also pointed out to me that if you want to make a supersaturation in moist air to a point that the water drops occur in liquid water drops occur in the absence of nuclei, that the amount of cooling you have to do varies with temperature. In other words, if you are up near the melting point of ice, you've got quite a high concentration of water molecules present, and so it doesn't take much cooling to make it become exceedingly probable that enough will be at the same place to form a drop. But he pointed out to me, I guess quantitatively, that when you get down to very low temperatures, below -40, I guess we were thinking about noctilucent clouds. At Liddy point, I thought that I do my thinking with certain assumptions that are sometimes exceedingly dubious, and I thought it was a kind of a law of nature, that a fourfold supersaturation in an expansion where you get water drops, and Liddy pointed out that that depends on what temperature you're talking about. And I guess when you, I don't know whether he had data on this or whether it had been calculated or whether he calculated it, but I guess that when you go down to very low temperatures, you need a tenfold. Well, it stands to reason. If you have scarcely any, why I have to go down to extraordinary low temperatures for it to ever happen. So this is something in my thinking that changed, and it's a place where I was wrong. And I'll confess to something even worse, and that is for a long time I got along using the assumption that the dry adiabat and dry expansion of dry air, why it cooled about 10 degrees C per kilometer of lift, and that's sound. And I thought that the moist adiabat was about was less, it was 6 degrees. But it took a while before it dawned on me that this moist adiabat depends on how much moisture you have there, and that the moist adiabat and the dry adiabat are identical when you get up to the top of a thunderstorm. And I feel better about this because there are people like Jim Telford who still invoke adiabatic cooling as the cause of downdrafts in thunderstorms. So I've got that off my chest.
I recall, you talked about this a couple of years ago, I believe, one of the letters to the editor that you've written.
I may have.
You talked about Telford and his work. I have no memory where it appeared.
Oh yes, I did write about Telford's statement on that. So I guess that's about it for the ice forming thing, and I don't have offhand think of something else in connection with that.
Well, we both know the final answer has not been said.
Yeah,
It's going to go on and on and on.
now, I don't know how long we've been going now.
I have not been checking the time either. It's, I would say 20 minutes. But
yeah, that'd be my guess. And I don't know about your schedule.
I've got another hour anyway.
You do? Well, let's give it a try. And you get into convection and convective electrification.
That would be good.
There's some relationship to this, of course.
Do you want to start how you came across this? Way
Yeah,
back
sure.
in the late 40s?
Yeah, I got became interested in electricity when I rediscovered the Rayleigh fountain, and found that I could influence the Rayleigh fountain at a distance by making space charge and having it drift down and cause it to bounce. So I understood that you could have charged air, I mean just transparent air, nothing that you could see, and that it could carry electric charge. And I got thinking about this. This is at GE, and I found that it was an easy thing to make charge air.
Before we get on into that, why don't you tell the story about you ran into C. Langer, I believe, when you made this discovery?
Yeah, when I found I had
You were quite excited.
discovered the bouncing fountain, then I'd gotten a stroboscope to get the details of what was going on, and then I found out that it was not nicely periodic, and I recognized what was happening, and I told Langner about it, and he laughed and thought it was funny, and referred me to Lord Rayleigh's publication in '79 or whatever it was. And so once I had a physical sense of space charge, right, and found that that's what streamed off of an electrode if you raised it to a high voltage. And the idea occurred to me that wouldn't it be fun to get a high voltage power supply and go outdoors when there's convection and turn it on and release space charge, which I figured would be would get into warm air that was going up, and that this charge that I was releasing would be carried up carried up high, or maybe into a cloud, and that this would be another form of a Van de Graaff machine, that instead of putting charge on a moving belt, I was putting it on updrafts, and it went up, and I thought, gee, maybe we could make a spark. And I asked around and found that there was a guy in the research lab that had a splendid DC power supply, and I visited him and told him of my idea and wondered if we could run an experiment in which I would put some wire or points or whatever outdoors at the research lab, and then we would run a line through his window and put it on his power supply. And he didn't get at all enthusiastic over this. And so the idea died.
Did you know anything about the work of C.T.R. Wilson at this time? Or the work that had been done in atmospheric electricity in general?
I knew scarcely anything. I had had a casual interest in what makes lightning, and I was aware somewhat of the precipitation idea. And I once asked Langner about it, and he showed me, explained, it may have been Wilson's selective ion capture, or it may have been the two German guys, whose names
Elster and Idle?
Elster and Geitel, whatever it is. May have been that. And I didn't think much more about it. Then I decided to leave GE and went to work at Arthur D. Little, where my friend from graduate student days, Howard McMahon, was. And when I arrived there, the way they work is that people come in with problems, and they pass them around, and then people say, well, gee, I think we could try this on it or something. That's the way they worked. And about the time I got there, there was a request for a proposal to do something about the dissipation of warm fog. It had already been shown that by cloud seeding you could clear up supercooled fog, and the Signal Corps decided to see what could be done to investigate the possibility of dissipating warm fog. And I was shown this, and I guess it may have been suggested that you wanted to make a proposal on this, and it looked interesting. And well, I was aware of Houghton's work, I assume in some detail, his dehydration of fogs with calcium chloride. And I knew that about Cottrell precipitators, and I guess that it occurred to me that maybe this could be done electrically, and I wrote a proposal to look into doing it electrically. I guess by that time I had begun to know, I guess, quite a bit about atmospheric electricity because I went to, while I was at GE, I went to London with Ted Rich on the stuff we were working on, detecting submarines with by the condensation nuclei. And Ted and I think, went to, what is it, the bookstore, Foyle's in London, a great big bookstore. And I saw Chalmers' first edition, so I bought that, and I had been reading some in it. I mean, I hadn't really gone into it much, but when we got I guess it's a contract at Arthur D. Little to look into fog dissipation, and I guess it was by electrical means, and so I really began to read this book, and so the Signal Corps put me through school in atmospheric electricity. And
I don't think Chalmers had anything to say, did he, about fogs in that book?
no, I don't think he did, no, but I think that the idea of dissipating clouds and fog electrically was certainly not new. And I decided to make large-scale electric fields in fog by releasing layers of space charge. And if I had a wire upwind, well, I could release space charge, and it would go downwind and make electric fields there, and maybe dissipate fogs. And eventually we did conduct, I devised instruments for making space charge, some just very dilute space charge, utilizing, when you put charge into the air, if you put it into the air as ions, why the ions see their image at the Earth, and they go to the ground pretty quick. But sometimes in nature there are quite a few aerosol particles, rather high concentrations, often from man's activities, and you can ride your charge on that. If you release ions and they become attached to these particles, well, then the mobility goes way down.
So the fast ions become the slow ions.
That's right, yeah. And those that don't go leave. And well, I also made apparatus that made aerosol, very small aerosol particles below the wavelength of light. I wanted to get as many as possible. And I made apparatus for producing concentrated aerosols and very strong electric fields. And that's all described in the literature.
As I recall, you used, like, diesel fuel?
No, I had a big old Buick engine from Howard McMahon's car, and I connected this up, connected the drive shaft to an airplane propeller, and this would make a nice blast of air, maybe a couple of meters in diameter. And I put aerosol in it by pumping. I had a pump attached to the engine, so that this pump squirted oil, crankcase oil, low vapor pressure oil, into the exhaust manifold. Okay. And this oil vaporized, and it was in the hot exhaust. And then I had an array of pipes with a lot of little holes in it, and I squirted the exhaust in fine jets out of all of these, and this made a smoke that, well, you could see sort of a purple haze in the bright sunlight, but it was sub-microscopic. And then I had a charger that consisted of cylinders several centimeters in diameter with fine wires between, parallel array, and then we blow the smoke through this thing and charge it up similar to a cottrell. And this highly charged smoke went out, and downwind of this thing there were strong electric fields, and you could, you held up your finger, you could get St. Elmo's fire, and St. Elmo's fire was coming off of nearby objects and coming off of the apparatus itself, and the opposite sign was being introduced into it, and cutting the charge way down. And then I had the idea of just after the aerosol had been charged, I made an array that made small water drops. It was a bunch of parallel plastic tubes, sort of garden hose. I don't know, maybe I just used stuff that was available that had little holes, and squirted out little water drops, I suppose, well, considerably less than a millimeter in diameter, but it's still pretty big. And the water came out as jets, and it was the droplets were inductively electrified with the opposite sign to the smoke. And then this was all blown downwind.
So they were suspended and moved downwind.
That's right. These water drops fell until they created a big enough field that they were levitated. And this stuff went downwind, and you can see the water drops dancing. It looked like insects. I guess the electric field was varying all the while. Well, we made attempts to see if we could make any effect on fog at Hingham, and we didn't feel that we did. And we've been going for what, 3/4 of an hour?
I would think so. The next thing is the Worcester tornado.
Hmm?
And next you had the Worcester tornado.
Yes, they, well, when I made the guess that maybe the convective motions of a cloud could build up, could carry charge and build up an electric field, and that the cloud could serve, could be much like a Van de Graaff machine with updrafts taking the place of moving belt. It also occurred to me that the cloud, like a Van de Graaff machine is a good electric motor. And if you supply a voltage to a Van de Graaff machine, why you can make an electric motor in which the belts are urged on by electrical forces. Let's see, could you reach that to me, I guess?
Oh, you're on.
Okay.
So, okay, yesterday I guess we got as far as talking about updrafts and downdrafts.
Yeah. I got this idea of an alternative mechanism for cloud electrification, a supplement perhaps to the transporter charge by falling precip. Essentially, I was proposing what I now recognize as transporter charge by falling air. And I gave this paper at the first conference on atmospheric electricity, and I wrote...
Now that was when, about 1952 or 3?
54, I think,
54.
something like that. And I wrote the thing up and sent it in to submitted it to a thing that later became jazz. I forget. It was a main publication of the AMS, and it got turned down. It was wrong for, one reviewer said it was wrong for any number of reasons. And the most important reason was that there aren't any downdrafts in the upper part of the cloud. And I guess Byers and Graham was cited, which had come out a little bit before. And I recognized that if that picture was correct, I guess was nonsense. And I couldn't get the thing published.
Now most of the other papers in the conference are supposed to be published in one place, weren't they? All the papers that were presented at that...
Well, I can't remember what... See, I submitted this independently to this AMS publication. I don't know whether that I'm quite sure was after the conference, and I think I submitted it. Well, when it came to the proceedings of the thing, well, I had submitted it there, and Sam Coronetti was in charge of the, he organized the conference. This conference was, Sam Coronetti got involved in atmospheric electricity because there was great interest in learning when the Russians fired off stuff. And so there was a lot of work in conductivity and so on. And this conference, where I gave the paper, the proceedings were published. And Sam Coronetti told me many years later that when they were getting these together, that here I got a proper name problem. This guy who at one time had been at New Mexico Tech. I worked with Workman, and he was a senior physicist, and I guess he was at UCLA something, and he was what, Holdsworth, it's not Holdsworth, I get it mixed up with Holdsworth, Holtzman, whatever, but Sam told me that when they were putting this stuff together, the proceedings, this guy said that there's no use wasting paper on this convective electrification. And Sam told me that he told this guy, well, after all, he was actually there and gave the paper, and so let's put it in. Well, Sam was in the driver's seat because the Air Force was paying for it. And so my paper did get into the proceedings. And well, they at the meeting, I think, it was brought up that that the mechanism couldn't work because there weren't any downdrafts. And I think there was some discussion about that. I was talking to Liddy, and he had been reading the proceedings, I guess, and was telling me that he found it interesting that there was some discussion there about it. Well, at any rate, I couldn't get the thing published on account of the, primarily on account of the downdraft business. Well, when Charlie Moore and I got together, we recognized that this was of great importance, the downdraft business. Charlie went over some of his balloon data, and he had a case where there was a balloon in a thunderstorm, and there were some downdrafts, not much to speak of, but there were some, and he published that. And then Joanne Malchus published a paper on cumulus clouds, and in which he talked about the downdrafts. And when that came out, I wrote a comment on it saying that I was very much interested in it because this was quite different from the Byers-Graham picture of a thunderstorm, in which there was nothing but updrafts. And there was an exchange in which Joanne had quite an extensive reply, gracefully dancing around everything, but still, I guess, standing up for the downdrafts. But
she had a reply to who now?
well, I wrote in for this thing and asked for how come that she had her article had downdrafts and Byers and Graham had none. And so each of them responded to my letter.
Okay, Byers and Graham and Joanne.
Yeah.
Okay.
And Byers and Graham, as I recall, their answer to this was that they had these three pictures of a thunderstorm: the cumulus stage, and then the mature stage, and then the dissipating stage. And they said that that actually that first stage, the cumulus stage, that was not to be taken for a cumulus cloud. That was not really a cumulus. As a matter of fact, that it was pretty damn high, and in the thunderstorm there, this was a reality, a thunderstorm at that time, and there were no downdrafts in the thunderstorm until the precip got going. Well, there was that exchange. Then I don't know, 5 or 10 years later, why there was this paper appeared, the Weather Bureau and NAC, I guess, Steiner and Rhines, they had a jet with accelerometers and stuff fly through thunderstorms, and 39,000 feet or something like that, and they had updrafts at 30 meters per second, downdrafts of 20 meters per second, and it was plain on the face of it that there were downdrafts, and I guess other stuff appeared. And it was so obvious that there were these downdrafts that Charlie and I didn't bother with it anymore. And I had, until just a few years ago, I had thought that this was ancient history. And, well, I mean, this question, all along, while there had been skepticism about the convective mechanism, and a lot of it centered about the circulation. but I guess about 3 years ago, Jim Telford took a swipe at convective electrification on the basis that there couldn't possibly be the downdraft required. And then I realized that that this idea of cloud circulation was still going strong, and then I looked in textbooks, and I see that, and articles, and I see that the Byers-Graham picture is still very much alive. I looked up in Mason's, B.J. Mason's second edition, and I don't know, it was 10, 20 years ago, but he discusses convective electrification and points out that it couldn't possibly occur because if you got a downdraft, it warm-ups, the fast couldn't do anything. Besides, you don't get any downdrafts until the final stages when the precip is formed. He don't think cited Byers and Graham, but I guess this is general knowledge, and I recognize that the Byers-Graham picture, the question about the downdrafts is still much alive, and then looking at stuff that Earl Williams was writing, he was questioning all this downdraft business, and I decided that to try to do something about it, and then I would look over the journals from time to time, and if I saw evidence of the Byers-Graham thing, I would write in comments on it. And I've done 3 or 4 of these things.
I think you've done more than that. In the past 3 years, I think you've done about 10.
Well,
these are letters to the editor.
Yes, yeah. And attempting to erode the Byers-Graham picture. And I hope that these are having some effect. I haven't had seen any comments on this in the journals, and I haven't had anybody write to give me encouragement. And
it seems to me, Bernie, in the past 3 or 4 years, in some of your letters to the editor, you have mentioned 2 or 3 papers where they did seem to find downdrafts. And you pointed out, here they are, these people have found the downdrafts. Why is this not recognized?
Yeah. Well, as a matter of fact, I'm hoping pretty soon to, I've got one that I think is going to be accepted in JGR, and maybe there'll be another one coming out in a while. And it may be sort of paranoia. I find myself thinking that virus and Bram are the ones that are principally responsible for the trouble I've had in getting anybody to pay serious attention to this suggestion. And I gave a talk in which I sailed in, a wonderful piece of luck. A few months ago was when Andre La Pena showed me this old book he had on weather, published in London in 1897, and it had a picture that was remarkably similar to the Byers-Graham picture.
I remember the day you found that. We were in John Scott's seminar class. You were sitting next to me, and Andre pulled the book over, and you were flipping through the pages. Voila!
Yeah.
Here was the picture.
Well, when I was wondering what I was going to say in San Francisco, you were suggested to me the use of alliteration, and I had not I barely knew what it was, and then I realized that it would be effective, and that I tried it at San Francisco, and I thought after I got back from San Francisco I'd shown the flag and I would quit worrying about this stuff, but I found I couldn't let go of it, and decided to write up something. And I sent in about a week ago.
Went to EOS.
Went to EOS, yeah. And I am hoping that this will get some attention, whereas the other ones I've been writing have not. And a few weeks ago I had a call from Bob Whitey, Kurt's friend in movie business, who's doing a documentary on Kurt, and who I guess was responsible for doing making a movie on Mother Night. And he's a very pleasant guy, and I was telling him about what I was doing, and I told him the title of this paper, a quaint cumulus conviction, and he remarked that I was getting into showbiz.
That's what you have to do.
Yeah, and I am hoping that maybe you get the right lattice fit. Looking back over the things I've been interested in, I see a common thread that I just love things where a little bit goes a very long way. And of course, cloud seeding is one of them. And I think that these comments being skeptical, pointing out the disagreement between this thing and others. Yeah, I'm hoping that that's sort of a gentle push, but this is a higher pressure applied at a point, and it may have the potential for initiating a fracture. Well, one of the things I worked on was the strength of glass, and
That was way back in the 1930s, I believe.
that's right, yeah, and that's a nucleation phenomenon. And if you have a freshly drawn fiber of silica glass, just melt sand, you can draw out a fiber, and it has amazing strength. You can extend it, I don't know, 5%. I mean, it's elastic. And the stresses are enormous. But I mean, it has enormous strength. But you just look at the surface, and then it is nucleated, and the strength drops by several orders of magnitude. And it's funny when you play with these things and stretch it. If you stretch it too far, you hear a pop, and then you notice on your fingers, and you'll see little silica fibers sticking out from them. That when the thing lets go, they must have some Christ awful speed, and they go right into the flesh.
I wasn't aware of that. Is this somewhat similar to the St. Rupert's Jews?
Indeed it is, yes. Well, it's the same thing. In the case of the extended fiber, it's all in tension, including the surface, and any weakness there, and the thing goes. But in the case of the Prince Rupert drops, the way those are made is by dropping molten glass into water or something, and chilling the surface very rapidly, while the interior is still gooey. And when it cools down, the interior shrinks and is much too small, and the exterior is in strong compression. And you can scratch that all you want, and it's not going to start to scratch because it's in compression. And there's what is called tempered glass, which are usually sheets of glass. It's sometimes done with bottles and cups and so on. What they do is, while the thing has just been formed and is, gooey, they direct jets of air on it. that cause cool the surface down, the viscosity goes up many orders of magnitude, and then the thing is under compression, and it is extremely strong. But if you do something that somehow gets down into it enough to get into the region that is under extreme stress, why then the whole thing almost explodes. And but here it's where just a little bit gets it started, and you cut a piece of glass tubing, making a scratch. Why? That's nucleation phenomenon. So that this is same sort of thing, and there are lots of things in nature where a little bit goes a long way, where you have an unstable situation, and if you know what you're doing, why you can create enormous effects with a very modest expenditure of energy and equipment, like a match in a forest.
I was just thinking of that.
Yeah, and it's my hope that maybe if this thing gets accepted by EOS, that it will initiate the breakdown of the Barres-Graham picture, not the Barres-Graham picture, that picture, that Victorian idea.
Yeah, I think the alliteration itself is a beautiful way to approach it. A lot of people are going to pay attention to that. And you just mentioned Victorian. I know you got the word Victorian in the text. And that goes along beautifully with the first word of the title, quaint.
Yeah.
Quaint, humorous, convection, convictions, and Victorian. That's a wonderful use of adjectives.
A lot of the good stuff in that paper comes from you and Sally, and a lot of it, I think, is quite a bit of accidental stuff in there.
I think you mentioned Scott. Didn't Scott?
And Scott, excuse me.
Victorian?
The
alliteration to start with, you had crazy.
Yeah.
And
Sally was right. I mean, that wouldn't.
Yeah, she came back with quaint. Yeah, she came back with quaint.
No, that was my idea.
Oh, it was, okay.
Oh yeah, no, she had
She didn't like. She didn't like the idea of crazy.
That's right, yeah, and she had another one, I forget, but then one night with insomnia, I came up with, I thought, a quaint. So it is quite gentle, really.
Oh, yes, it is. Yeah. Except the rather interesting title. And that may be the fracture that will nucleate something in the future.
Yeah.
Well, Another thing that may nucleate something too, I know in the past few years you've been trying to get experiments going to put chaff in the top of clouds.
Yes.
Here is a wonderful way to experimentally show there are downdrafts.
Charlie Moore and I recognized this soon after we got into this business. But you could do that in a cumulus. We already knew cumulus had downdraft. But it had to be shown in a thunderstorm, and you couldn't do it in a thunderstorm because you couldn't tell the difference between the